Okay, hello everybody. We're week 3, Calc 1, day 12, chapter 4, section 1. We are definitely moving over the hump now. So today we're going to start looking at the concept of why we need antiderivatives and integrals. So first we're going to, just like the derivatives, go through some of the meat of the substance to understand why we do what we do. So first thing we're going to talk about is area problem. So you know that when you have area, you can find area of a triangle, length times width, area of a rectangle, let's say triangle, rectangle, length times width, triangle, 1/2 the base times the height. Or you could have something like this where you break it up into parts and then add the areas together, and this is significant to what we're going to take a look at. So the problem is, how do you find the area under the curve? How do you find the area under the curve? Very important problem in applications, as we'll see as we go through chapter 4. But how do we do that? We don't have a set figure like a rectangle or a triangle or anything like that. So this is what we do. Let's look at the basic parabola curve. Here we have y equals x squared, and here's our point 1, 1, just our parent function of a parabola. And what we could do is we could break this down into 4 parts, we'll say. And I'm just saying 4 parts to start off with. And so if I have from 0 to 1 here, this would be 1/4, 1/2, 3/4, and 1. So with that being said, I could have 1, 2, 3, 4 areas that I need to add together to get my area of the whole thing. So there's a couple ways that we can do this. One is to estimate by making rectangles, and when we do it this way, we call making a rectangle from the right endpoint, because this endpoint here to go over this way, and then come up to this endpoint here to go over here, and then this endpoint 3/4 to go over here, and this endpoint to go over here. Now you can see by looking at that it's going to be bigger than we need it to be. We're going to be adding all this stuff above here that does not include the area under the curve, so we need to make some adjustments to that. So then the idea would be, well, let's look at if we do it the other way. Let's look at if we do the rectangles from the left endpoints. And when I do that, I have a 0 height here, I have 1/4 height here, I have 1/2 height here, and 3/4 height here. So then again, you can see the issue is that now we're too little. So the first one was too big and the second one was too little. So you might say, all right, well, I can at least say that my area is between the two. And that, in fact, you can. So here's my smaller and here's my larger, and I could say my area is going to be greater than this or less than my first one over here. Okay, so we have these two still on the screen here. All right, so there's an idea. So then we start thinking, well, what if we break it into smaller rectangles? So if I start breaking it into smaller rectangles, you can see that my estimate is actually going to get quite a bit closer. So here I have 1, 2, 3, 4, 5, 6, 7 rectangles. 1, 2, 3, 4, 5, 6, 7, 8 rectangles. 8 rectangles, and I'm going to do the left and the right endpoints. So this is from the left endpoints, and this is from the right endpoints. And we can see that now we're a little tighter. See, before when we did the 4, we had 21875.21875 as my smallest and 0.46875 as my largest, and the area was somewhere in there. Now that I have 8 rectangles, it narrows it down. So I'm at 0.2734375 here and 0.398 0.4375 here. So you can see that's quite a bit different. Now, before we go on looking at more, let's look at actually what that looks like as an equation. Okay, so a rectangle would be length times width. And remember, our formula here that we're looking at is y equals x squared. It's the parabola. So if I take a look at the first one, from the right, we'll say from the right endpoint. So from the right, I'm going to have right here, I have 1/4 times whatever this height is, which would be 1/4 into f of x. So f of 1/4. So f of x is x squared. So that's why this length times width would be, or the width times length, I'll say, since the length is higher, width times length. All my widths are 1/4 because that's what I broke it down to be. And then my lengths are that endpoint that we're looking at into f of x, or y equals x squared in this point. So I'm going to have 1/4 squared, 1/2 squared, 3/4 squared, and 1 squared when I use my right endpoints. And then when I use my left endpoints, I'm going to take a look at 0 squared, 1/4 squared, 1/2 squared, 3/4 squared. Okay, not 1 because I don't have a rectangle here. So that's how I get these two, is I'm actually using the sums of the areas of those rectangles to get that, to get those solutions. And then I would do the same thing, which you can see could be a bit tedious here if I'm going to do the 8. Now, there's a chart down here at the bottom. It says, well, let's see if you have 10 rectangles. Let's see if you have 20 rectangles. What about 30 rectangles, 50 rectangles, 100? What about 1,000 rectangles? Which I wouldn't want to add up 1,000 rectangles. But, you know, we can use computer programming to take a look at that. And you can see as we get closer and closer to infinity, I get closer and closer to my answer. So we are in fact going to be looking at a limit here. You can see these two are much more similar now that I have 1,000 little rectangles. Let's see what those look like. Here on this page, I have my 10 rectangles, my 30, my 50, and these are all from my right endpoints. So that's what the R of 10 means. The R of 30 and R of 50 means my right endpoints. And then my left endpoints, I have again 10, 30, and 50. And you can see as I increase my rectangles, I get closer and closer, definitely closer and closer to my actual sum. Okay, so now we'll jump back to example 2. I'm going to take a look at some patterns that we have here, and we will use these patterns when we are solving some of these equations. So here we have the sum of the areas of the rectangles. Each one has 1/nth width, y/nth. Well, if I'm dividing 1 by 10, I'd take 1 divided by 10, and that's going to be the width of each of my rectangles. So that's my width. And then my height is going to be, if I place that number in for x and get x squared. So I have here 1 over n squared, then 2 over n squared, then 3 over n squared. And you can see this definite pattern here. And I can factor out my 1 over n, and I can factor out a 1 over n squared. And when I do that, I will be left with 1 squared plus 2 squared plus 3 squared, and we have this definite sum pattern right here. So we need a formula for the sum of squares for the first positive and positive integers. This way, now we don't have to add all of those 1,000 triangles or rectangles. I don't know why I keep saying triangles. Rectangles. And here is my formula developed from this concept, n times n plus 1 times 2n plus 1 all over 6. Okay? Now, it says you may have seen this formula before. It was proved in example 5. Here we go. Taking a look at infinity. As n approaches infinity, what happens there? As n approaches infinity, well, I'm going to divide everything by 1 over n cubed. Why n cubed? Why n cubed? Well, n cubed because I have n times n here. So the highest degree would be the third power. So when I'm dividing by n cubed, I will then get this as it approaches infinity, and I'm going to split it up a bit, and after I do that, as it approaches infinity, I will see that this will become 0 and this will become 0, so I end up having 1/6 times 1 times 2, and I see that I will get 1/3. So it can be shown that as it approaches infinity, that my area under the curve of that parabola from 0 to 1 is 1/3. Keep in mind, 1/3 is 0.33333. And as I look at my estimates over here at the bottom of the page, when I was going to 1,000, I can see that is what I am approaching, is 0.3 repeating. Okay? So, thank goodness we have some shortcuts and we don't have to add up 1,000 rectangles. Now, let's apply this to the idea of examples 1 and 2. We have, it's not always going to be some nice little parabola curve. We might have something like this. So let's take a look at that. And again, we're going to split them into equal widths. So the widths would be the same, and we're still going to be looking at rectangles. So what would the width of the interval be? Well, that depends on what you're starting and ending at. So if I'm going to say I'm going to look at this from A to B, just like before, the parabola was 0 to 1. Okay, the parabola was 0 to 1 that we looked at. We'll flip back here, 0 to 1. Now I'm saying, what am I going to look at this at? Well, I'm going to look at it at from A to B. So generically, I'm going to take my B minus A to get my width, and then I'm going to decide how many rectangles I'm going to break it up into. So my width value, delta x, is going to be this divided by n. So these little strips will have these intervals from x sub 0 to x sub 1, x sub 1 to x sub 2, x sub 2, x sub 3, etc., depending on how many rectangles I have. So here's what that might look like. Here I have my right endpoint looking like this. Now this is kind of nice because I'm like, well, you know, I'm a little bit low here, but I'm a little bit high here. This kind of makes up for this area. I'm still not going to be exact, but it's looking a little better. And looking at how many rectangles I use, if I use 2, not a very good estimate. If I use 4, maybe a little better estimate. 8, 12, and once again I see as I approach infinity that I'm going to get the better answer. Now, as in mathematics, we like to always see if we can improve things to be better and better and better. So one of the things that we do after we define this area, we said the area will be the width times the height of the sum of all of those rectangles as n approaches infinity. Then somebody said, well, why do we have to use right endpoints and left endpoints? Why can't we use a point that actually hits the graph? That would probably give us a much better area. So instead of using the right or left endpoint, I'm going to use the endpoint or the point x sub 1 where it actually meets the graph. So instead of using A or x1, I'm going to use this right here, whatever this value is. So that would make it a little better. And these are called sample points. And this is their symbol, x sub 1 with a little asterisk above it would be sample points showing approximating rectangles when the sample points chosen are not endpoints. So we use this notation when the points are not endpoints, they're other points, okay? All right. Now, I'm sure you have been familiar with sigma notation, but they're reintroducing it to you. For sigma notation means you're going to add all of these areas together, the sum of all the areas. And then they're pointing out that you could add the sum of all these areas together. The other way of expressing it would be as n approaches infinity from 1 to n using the summation of f of xi, and then you have your delta x. Remember, your delta x is your width. So looking at these formulas, we can rewrite the formula 1 that we looked at in the way of this, where we use the sigma sign. Sigma as I approaches, or as I goes to n times I squared, and we have this formula here. Okay, example 3, let area be a region under the curve of cosine x between 0 and b, where b is between 0 and pi over 2. So x equals 0 and x equals b. We're going to use the endpoints for the expression of the limit. We don't have to evaluate the limit, but we're going to estimate the area. In the case of b is pi over 2, take the sample points to be midpoints using the 4 subintervals. So since a equals 0, we're going to have b minus 0 over n. Okay, b minus 0 over n. So my x sub 1 is b over n, my x sub 2 is 2b over n, x sub 3, 3b over n, etc. Using the sum of approximating the triangles, my f of x is cosine x. That's the function that I'm talking about. So I'm just replacing this here, and then x sub 1, x sub 2, etc. To the end. So now I'm going to say, what value is that? Well, up here I said x sub 1 is b over n, x sub 2 is 2b over n, and then I'm plugging that in as well. Now, according to definition 2, the area then would be this b over n. I'm going to factor out times my cosine of b over n, cosine of 2b over n, cosine of 3b over n, etc. And using sigma notation, I then can write this out as n approaches infinity, b over n, again my width, as the sum of 1 to n, how many ever rectangles you have, cosine of IB over n. So there we go. And they say it's kind of difficult to do this by hand, so you use a calculator here. Now let's take a look at what that graph looks like. Here we go. Now we have 0 to pi over 2. And we're pointing out that we're going to use our values here where it actually hits the graph. So my x sub 1 is going to be pi over 16. So we're saying that this value right here is pi over 16. And x sub 2 is going to be 3 pi over 16. X sub 3 is going to be 5 pi over 16. And x sub 4 is going to be 7 pi over 16. Okay, when I plug everything into my summation, I'm going to place pi over 16 into my cosine value, and then I'm multiplying it again by my width. My width is still pi over 8. And the estimated area for this would be 1.006. Okay? Alrighty. Alright, now we're going to take a look at a distance problem. So let's look at a little bit of an application here. Now we're going to consider distance problem. Distance equals velocity times the time. So here you have an odometer and your car is broken, but we want to estimate the distance driven over a 30-second time interval. So we take the speedometer readings every 5 seconds, record them in the following table. Okay. In order to have the time and velocity in consistent units, let's convert the velocity readings to feet per second, knowing that 1 mile is 5,280 over 3,600 feet per second. So this is the conversion. Okay, so velocity during that time interval would be the initial velocity and the approximated distance during the first 5 seconds. So each interval, the width is going to be 5 seconds. Similarly, here's the next 5 seconds. And as we continue through, we're going to add those together, each interval times the width, which is 5 seconds. Now, they point out you could have used the velocity at the end of each time period instead of the velocity at the beginning. Then your estimate would be here. So your actual answer would be in between this and this. Okay, so this would be your left hand and this would be your right endpoints. Okay, and that's pretty much it for this section. We're going to take a look at section 4.2, but area under the curve is why we are going to start studying integrals. And so, of course, it's important for you to know the background of it, and that's what we did today. So, I will see you for section 4.2. Hope you have a great day.